Dear students, in last class we studied short transmission lines performance. Today, before we go for medium transmission line, we will take generalized circuit constants. A transmission line can be represented by a two-port network which will be having 4 terminals as shown in figure below. On left side we are having sending end terminals, and on right side we are having receiving end terminals. So sending end voltage is Vs, sending end current is Is, receiving end current is IR, and receiving end voltage is VR. This side we have sending end, and here on this side receiving end. A transmission line can be represented as 4-terminal or 2-port network. As shown in figure above. This 2-port network is passive. Passive means it won't contain any energy sources. And bilateral. Bilateral means impedance is independent of direction of current flow. For such a two-port network, we can write the relationships between sending end voltage, receiving end voltage, receiving end current, and sending end current, receiving end voltage, and receiving end current. As Vs equal to A into Vr plus B into IR. Is equal to C into Vr plus D into IR. Let us call this as equation 1 and this as 2. Now these two equations we can write in matrix form as column matrix having Vs and Is as two elements, square matrix having A, B, C and D constants, multiplied with column matrix having elements Vr and Ir. Now let us call this as equation 3, where A, B, C and D are generalized circuit constants and hold the following properties. One, these are complex constants. That means they are of the form A plus BI. Second one, they hold AD minus BC equal to 1. Third one, if symmetrical network then A equal to D. A and D are dimensionless. B is impedance, C is admittance. You can observe equation 1 and 2. Vs is equal to A into Vr. That means voltage is equal to some constant into voltage. Therefore, definitely A is unitless quantity. That means it has no dimension. Whereas B into IR we are having here in second term. Voltage is equal to impedance into current. Therefore, B should be definitely having unit of impedance, that is ohm. And in second equation we are having Is equal to C into Vr. We know that current is equal to voltage upon impedance or admittance into voltage. Therefore, the unit of C is that of admittance, that is mho. That is mho. Current equal to current into constant. Therefore, definitely D must be unitless quantity. Now, we will give the proof for AD minus BC equal to 1. Consider figure below where an ideal voltage source ideal voltage source means its internal impedance will be equal to 0. With 0 internal impedance is connected to sending end. And receiving end is short circuited. With 0 impedance. Thus, Vr is equal to 0 and using equations 1 and 2 we can write Here is the two-port network. To the sending end terminals, we have connected Vs. Current Is is flowing into the sending end terminals. Receiving end terminals are short circuited with zero impedance. Therefore, Vr equal to 0. That is, receiving end voltage is equal to 0. But IR will not be equal to 0 as there is path for current to flow. And this IR will be now quite high because impedance is 0. So in equation 1, where we have written Vs is equal to A into Vr plus B into IR. If I put Vr equal to 0, then A into Vr will become 0. Therefore, Vs will be equal to B into IR, and that is what we have written here now. Right? And from equation 2, Is equal to C into Vr plus D into IR. Vr is again equal to 0. So Is will become D into IR. Is will be equal to D into IR. And Is is equal to D into IR. Therefore, we can now write IR equal to Vs by B. Let us call this as equation 4 now. We know that the two-port network is bilateral, assuming that it is symmetrical also. Suppose the sending end is short circuited and the same ideal voltage E. The same ideal voltage E, it means Vs equal to E also. If Vs equal to E, I can write here E upon P is applied to the receiving end terminals. As shown in figure below. From equation 1, that is Vs equal to A into Vr plus B into IR. Substituting for Vs equal to 0, we get A into E, because receiving end voltage is E, plus B into IR. Or IR equal to minus AE by B. Let us call this as equation 5 now. You all are learning network analysis, so you must have studied reciprocity theorem. So I'll write here, using reciprocating theorem, Is equal to minus IR. From equation 2, Is equal to minus IR equal to C into E, because receiving end voltage is equal to capital E plus D into IR. Using equations 5 and 4, you can write minus IR equal to CE minus D into AE upon B. Minus IR equal to AE into B we have written in equation 5. Simplifying, we get that is equal to minus E by B. This we are writing using equation 4. In equation 4, what we have written? We have written IR equal to E by B. Now I will take RHS of this equation as CE minus D into AE upon B equal to minus E by B. Taking E common outside, C minus dA upon B equal to minus E by B. Now E and E will cancel, giving out minus 1 here. So taking B to the LHS, we get BC minus DA equal to minus 1. Multiplying on both sides by minus 1, we get minus BC plus AD equal to plus 1, or AD minus BC equal to plus 1. Or AD minus BC equal to plus 1. This relationship is very useful in checking the values of A, B, C and D which are calculated independently. Next we'll take ABCD constants in terms of receiving end quantities, that is VR and IR. At the same time, I would like to call this as equation 6. Sometimes it may be necessary to represent the receiving end voltage and current in terms of sending end current and voltage with the help of ABCD parameters. Now we will see how we can relate VR and IR with Vs and Is using ABCD constants. Right here, pre-multiplying equations one and 2 by C and A respectively, we get C into Vs equal to A into VR plus B into IR, and A into IS equal to C into VR plus D into IR. Let us call this equation as equation number 7 and this as equation number 8. Subtracting equation 8 from equation 7, we get C into Vs equal to AC into VR plus BC into IR. A into IS equal to A into C VR plus AD into IR. These two will cancel here and we'll have C into Vs minus A into IS equal to IR into the bracket BC minus AD. Since AD minus BC equal to 1, I can use BC minus AD as minus 1. So, C into Vs minus A into Is equal to minus IR. Or IR equal to, by multiplying by minus 1 on both sides, we get IR equal to A into Is minus C into Vs. Now, pre-multiplying equations 1 and 2 by D and B respectively, we get D into Vs equal to AD into VR plus BD into IR B into Is equal to BC into VR plus BD into IR. Let us call this as now equation let us call this as equation 9. Let us call these two as equations 10 and 11. Subtracting 11 from 10 and using AD minus BC equal to 1 again, D into Vs minus B into Is equal to Now these two terms will cancel. We will have AD minus BC into VR. But AD minus BC equal to what? It is equal to 1. So 1 into VR is VR. So D into Vs minus B into Is. Or we can write VR equal to D into Vs minus B into Is. Let us call this as equation 12. Now we will write equation 9 and equation 12 in matrix form. Writing equations 12 and 9 in matrix form. So equation 13 relates sending end quantities with equation 13 relates receiving end quantities with sending end quantities using ABCD constants. Dear students, I will stop the class here and continue in next class. Thank you.